All right, good afternoon, everybody. Welcome. I hope we're recording in the back there. Thanks for coming after that big, heavy lunch. They kind of force you to stand up while you're eating it, so it kind of goes down a little bit more quickly. This is the forced DevWeek logo on the first slide. And I'm going to switch to the actual slide that has this nice, cool little animation. We're going to be talking about this thing called programming in the fourth dimension, and this is the little icon that I like to use for talking about the fourth dimension. For those of you who aren't familiar with this is a four-dimensional cube. It's called a tesseract. You can search on Wikipedia and read all about it. The reason that I use it clearly in terms of fourth dimension is because it has this element of time. And the thing about this, and don't stare at it too long, it'll kind of turn your brain to mush, because your brains aren't really wired for this kind of stuff. It's a cube that over time is kind of folding in on itself and turning into the same cube. And that's really going to be the topic of this next hour and a half together, is talking about the element of time when we're programming. Starting from the very basic stuff that I hope everybody knows and quickly checking that off, and moving to the more interesting elements of time. Now, full disclosure, when I went to uni, I failed the course on relativity twice. Okay, so I'm definitely not the expert when it comes to how different objects change their mass and how speed and time, all of that is interrelated. We're going to take this from a very much more basic programming perspective. And from there, we're going to move on to different ways of thinking about time, programming about time, requirements analysis, and ultimately we're going to implement things, some patterns that you can use, and frameworks that support those patterns to get you guys up and running really quickly. So, starting off with the absolute basics, date time now is evil, okay? It is just about the most evil thing that you can create in your system, which is why Microsoft made it part of the base class library. Because I mean, it's so trivial to just immediately start using it, and it compiles, it runs. Even if you write some unit tests, there's a pretty good chance that those unit tests might even pass. But as things start to take a little bit longer, then comparing date times to each other starts to break down. Because if enough ticks go by between when you set date time now, for example, in a unit test, until when you actually used it in your code, then your unit tests fail. And that's actually the good news, is when you actually have a unit test that's doing that, because then it will be an indication that when your system ends up in production, this is going to be a problem. All right? Now, so number one, anytime that you yourself are writing code that's using date time now, or you see anybody else writing code, give them a nice little slap on the wrist, or program something into their machine to give them an electrical shock when that coding pattern is matched. One of the nice things that Microsoft has coming out in VS 2013, if you haven't heard about it, it's called ROS1. It's their compiler as a service feature, which allows you to write little rules to be able to say when somebody writes a certain bit of code, whether you want that code to be allowable or not. So eventually I'm going to get around to writing a rule on top of the compiler as a service, so that every time that somebody writes this, their code will not actually build. Okay? So what's the problem with that? Well, you need to take a step above that. UTC now is a little bit better. It's kind of, it doesn't look evil, and it kind of pretends to be nice, kind of like these guys over here. But if you get into the details, even there are some minor problems. So UTC now ultimately is saying, first, we're dealing with the issue of time zones. Okay. So when you're talking about a system that needs to be deployed to more than one server, and let's face it, most software these days is not only ever going to run on a single machine, then you have to deal with the issue of time zones. More specifically, the fact that not necessarily are all the machines that are in your server farm going to always be set up in the same time zone. This becomes more of a problem when you have more than one data center or more than one administrator, or if somebody's actually changing the time zone of the machine. Something small like that can cause your code to start working in weird ways. So next step up, make sure that in every place that you are going to do something with date time now, replace that with UTC now, and that will help you take a step forward. The other issue to deal with is anytime that you're thinking about time in your system is the whole issue of daylight savings times. As we know here in the UK, we have recently moved turning on daylight savings time. And, but of course, that's out of sync with the rest of the world, right? Different countries decide or decide not to observe daylight savings time at different points in time, and also that changes from one year to the next. So I think it was last year or 2 years ago that Argentina decided all of a sudden that they were not going to observe daylight savings time. It's just, presidential order, no daylight savings time this year. It's kind of hard to code for those situations. So you will want to understand that anytime you're doing something with time and your users may be in some part of the world that decides unilaterally to not observe daylight savings time or to observe it on a different day, again, your code can start running in weird ways, especially if you have things that, some part of your system is running in time zone A, persists some data to the database, something else is reading that out, and is assuming that it's in the same time zone, it's in the same daylight savings time setting. This is the kind of stuff that hardly ever pops up in testing because nobody ever thinks to fiddle around with time zones or daylight savings time on machines while they're testing the system. So it's something for you to think about, just to kind of get your frame of reference of how long we in the software industry have been having support in our programming languages for operating on date, time, data structure type things, and the fact that the problem isn't solved yet today, okay? And really all I can tell you is if we haven't solved it up until now, we're probably not going to solve it by the time your project is done, okay? So this is nice big risk for you to go back and say, what are we doing about it? Now, the next step up, for those of you who are thinking of running in the cloud, is the topic of clock skew, okay? And this is true for almost every geographically distributed system, that different machines that are in vastly different areas on the planet, you can't keep them 100% in sync in terms of the clock. So there is network time, etc., but the way that machines drift from each other in terms of, it's called clock skew, is really unknowable. So if you want to build a system that is absolutely bulletproof in the cloud, running in multiple availability zones, then you're going to have to totally stop using the concept of clocks or time that is built into base class libraries or the runtime. And you're going to have to come up with your own representation of time. Amazon did this a while ago, wrote a very nice paper on it, called it Dynamo, which served as the backbone for their Amazon DynamoDB, where ultimately everything is tracked with, they call it vector clocks. You could think of it as a kind of large version number. However, the challenge around that is when you're building geographically distributed systems, is when you can no longer count on time and you've got all of these funky little vector clocks, your programming model kind of turns on its head, okay? So we're not going to be talking in this session because this is like 5-day course material. This is not 50-minute material. Just to give you a sense of the fact that, again, this problem is, not only is it not solved, but the bigger the system we try to build, the more unsolved it fundamentally is. And the more this problem becomes your problem, and again, the bad news being that when you're building a system on your own machine, everything works fine. When you're running all of your unit tests and you're kind of fiddling, everything works fine. And it's only when your project is 99% done and you're 2 weeks away from going to production, and things are installed and now things are working weird, that all of a sudden you start tracking it down and you find out that for whatever reason, when you spit out the clock ticks of the various time zone pieces, they're not in sync the way that you thought that they are supposed to be. So that's just to tell you that I like to start my talks with bad news, okay, to get people in the right frame of mind. Software sucks, okay? Programming, you might think, oh, cool, we've got the cloud and we've got all of these libraries and frameworks and it makes programming more productive than ever before. Like, yeah, but the problems that we're trying to solve are growing so much faster than the tools that we actually have available that we're actually falling farther and farther behind compared to where we were 3 years ago, 5 years ago, 10 years ago. Okay? So now on that optimistic note, let's talk back on the requirements side of things, where even if you're in a case where your entire system is co-located and all the machines are in the same time zone, and you're under the most ideal possible conditions, even there are some risks around how you go about handling requirements that explicitly talk about time. So one of the places where we see a lot of these is batch jobs. Who's got a batch job in their system? Yes? Okay, a bunch of you. Now, batch jobs are kind of like the black sheep of the family. Nobody really loves them. The code is kind of, it's kind of handed off to the most junior developer. Here, write this batch job, clean that crap out of the database. It doesn't have to be that elegant. If you don't TDD, BDD, DDD, if you don't DD it, you're fine. Just kind of make it work. So you get all of this code that's going to go into the database, scanning through a list of something and said, if something happened in the last 24 hours, then do this. If something happened in the last 3 months, then do that. So a lot of time-based requirements, you don't necessarily see them kind of glaring in your face in the online transaction processing part of your system. A lot of times they're kind of sitting there in batch jobs that are pulling the database once a night, and then in there they're kind of checking time-based things. And again, the problem being that it's often written by the most junior people in the team, and that code isn't really thought of as part of the system. So if you make changes to the logic in the part of the system that's writing the data to the database to begin with, oftentimes we forget to handle the batch job part of the code as well. So even if you don't see it glaring in your face where your business is saying, hey, look, here's a time-based requirement, sometimes go look for it in the batch jobs and you'll actually see quite a lot over there. So we're going to take one as an example from the retail domain. I love the retail domain because most of us have had first-hand knowledge and first-hand experience as users in this domain. So classical example is you bought a product some time ago and now you want to return it and get a refund. Okay? So fairly simple type of requirement. And now the business says, look, we have these rules that say under which conditions will the end user get a refund for returning the product. So it could be really simple stuff, starting out with something like this. Here's some pseudocode type stuff that says, all right, well, when you get the time that the product was returned and you know when it was purchased, check to see if it was in the past 30 days. So if somebody returns their product within 30 days of a purchase, they're going to get 100% refund. If they return it within 60 days, so between 30 and 60, then they get a 50% refund, otherwise no refund at all. So it's the kind of logic that, again, you can have batch job going into the database, looking at the times that products were purchased, the time that they were returned, and then performing this fairly simple calculation and then deciding, okay, this one is eligible for a refund, that one isn't eligible for a refund, and we're done. Now, this sort of code, easy to implement, easy to test. I mean, you write a unit test for this and check that, okay, we did 20 days, we did 40 days, we did 90 days, everything works out okay. Even if you keep this code is fairly nice and clean. It's not as horrendous as some batch job type code. Good separation of SQL type lookups from the actual logic of doing things. But there's actually a dangerous bug in this code. And what makes this code wrong, or I'd say more specifically, it's dangerously wrong, is code that looks right and works correctly most of the time, but when certain things happen, then it starts to behave really wrong. So what's wrong about this code is how it behaves when requirements change. So when the business comes to us, so the system's in production, it's been that way for 6, 10, whatever months. And the business says, we'd like to twiddle it a little bit. What if we changed the time frames from 30 days and 60 days to 20 days and 40 days? We, the developer, well, we don't really give a damn one way or the other. You know, come up with the rules, tell us, we'll implement it, and off we go. So they say, okay, yeah, do this. So again, junior programmer changes 30 to 20, 60 to 40, sees that, you know, everything is working the way that they expect, and they deploy it into production. And for a while, it looks like everything's okay. The danger, if you will, is how the system starts behaving from an end user perspective. So let's plot things out on the dimension of time. So let's say, you know, version 1, we went into production with these rules that said it's 30/60, and the system's running for a while, and on and on and on and on. And then at some point in time we go to V2 and the rules are changed. What happens if a customer made their purchase while the system was in V1, okay? And then a certain time after that purchase, you go and deploy V2 on them, and then they want to return their products afterwards, okay? So you are the customer, you made a purchase in the system while it was, I mean, when you're using a web-based system, you don't know what version it's running, and you shouldn't really care. And then 50 days you come back and say, yeah, I'd like to return my products. And you know, that the code that we just saw starts running, and it says, nope, sorry, no refund for you. And you're saying, wait a minute, I'm pretty sure that when I made my purchase, you told me that the rules were 30/60. But of course the code doesn't really care, you can't argue with code. It said, no, really very simple, you know, you returned it more than 40 days later, and our rules state if you return your products in a time greater than 40 days, no refund. This is what I mean by code that is dangerously wrong. It looks right. It passes unit tests. When you put it into production, it doesn't blow up in a big, you know, ball of fire. Everything kind of looks okay, and that's the dangerously wrong part of it. We're all very on edge, right? You deploy a new system to production, kind of like, is this going to work? And you know, an hour goes by, and you know, nothing's blowing up. And 2 hours go by, and you know, you're watching the performance counters on the server. Oh, it looks like everything's okay. Kind of let out a sigh of relief, and you're kind of still watching the system. To 3 or 4 hours, and I'm like, okay, I think that's it. I think we can go home. So you go home, and a day goes by, and still, you know, no big gigantic problems. But as more time goes by, the likelihood of something like this happening increases more and more. And then, of course, when it becomes a thing, customers, you know, imagine that this is not just one of you, but you know, 10 customers and 50 customers start complaining over Twitter and Facebook. They're like, yeah, I returned my products and didn't get a refund, and they said they couldn't change it because that was their policy. And then you know, you get this sort of build-up, and all of a sudden your company is looking really, really bad. You know, you call yourself a customer service company. Why is it that you're breaking your own rules around how people get refunds? Now, again, this is a very simple, almost synthetic example of fairly trivial business rules. But you can imagine as your rules get more complex, you have more calculations related to time, it becomes more and more difficult to actually tear these things apart. So how do we handle this? So how can we write code in such a way that it won't be susceptible to these sorts of problems? Now, there's no magic solution, but ultimately what we need to do is we need to take, using that time zone example, we need to think of our system as operating in multiple frames of time, and we as developers need to take a different perspective of time, rather than just kind of looking at it from the perspective of, again, as I said on the first slide, date, time, now. So that element that everything's always looked at from the perspective of now. What we need to start looking at, saying, well, actually, there are multiple frames of references and multiple perspectives that we can take on time. So the problem that we have with the rules as they were originally specified is that they're looking at things from the perspective of, when the products were returned, looking back to when they were purchased, right? And then doing a calculation based on that. But in essence, what the rules are telling us is that looking at this diagram, you actually have to look forwards in time. That the rules are not so much a calculation as to what happened in the past, but they're a promise towards what will happen in the future. Okay? So in talking about these different perspectives of time, in essence, we need to take either a future-oriented perspective of time, meaning this is a promise towards future behavior, or, and differentiating that from requirements that are a historical perspective of time, saying, okay, from now, look back, do this. And this is not the kind of thing that when somebody gives you a requirement that they'll tell you, okay, this is what I mean by it, that this is a future time reference or this is a past time reference. You have to go and ask. Now, one of the words that I sometimes use to kind of help trigger the business stakeholder to give me the answer the right way, say, when the rules change, going back to this picture over here, when you tell me that the rules change, do you want this change to be applied, and here's that word, retroactively? Okay, when you say the word retroactively, or at least in my experience, every time I've said that, the business stakeholder hears that, they're like, wait, let me think about that. What exactly does that mean? Well, when we change the rules, applying them retroactively means anybody who performed an action in the past, the rules would apply to them. Okay? And that's an important question. Is this something that needs to apply towards things that have already occurred in the past? Or is this really, from now on, everybody in the future is going to behave according to these rules, but whatever happened in the past needs to continue behaving according to the old set of rules. And this can kind of put us in a bind, because in essence, we need to have a system that can operate on two different sets of rules at the same time, right? So if a customer made their purchase over here and they're doing their return over here, they have to be calculated according to V1 rules. However, if a customer made a purchase at the time of V2 and then they return it shortly thereafter, then they need to get the V2 rules. So we need to have some way that we can have V1 rules and V2 rules happening at the same time in the same system. That's not something that, versioning in software is by itself a hard problem to solve, right? Countless times that we have, all sorts of deserialization problems because we changed the contract in a way that wasn't backwards compatible. But now we're kind of taking things even a step beyond that, saying, well, even after you solve all of those problems, now you have to design the system in such a way that it can actually run two sets of rules at the same time without really knowing in advance, when somebody's returning a product, how do you know that they purchased it on V1 or V2? It's not something you can kind of partition and say, oh, I know, when you made the purchase, you made it on V1. We can kind of try that, say, well, we'll put it in a cookie. That every time a customer makes a purchase, we put the version number that the system was on in a cookie, and then the next time that they submit it, we pass that cookie along, and then we can know to route that to version 1 of the system or version 2 of the system. So you can kind of try to do that. It becomes more difficult, again, if this is running in sort of a batch process off the back end, or any type of asynchronous processes, it becomes more challenging to handle that. So, in essence, what we're going to be talking about here is how do you program the future? Okay, how can you build a system in such a way that you can have rules that apply, that are defined now but will be applied in the future, even if the system is running a different set of code now. So anytime that you're talking to your business stakeholders and they tell you that this is a future-oriented requirement, meaning it's a promise, okay? If this is a promise that we will do something in a certain way in the future, then we need to look at things not from the time that the products were returned, but the time that the users triggered this type of, you could think of it as a kind of long-running process. That when they made their purchase, in essence what we want to do is we want to toss into the future this element of, if you return your products in this time window, then your refund will be 100%, but we need to encapsulate that and store it in such a way that even if the rules change, that will apply. And same thing, at this point in time, we toss into the future this 50%. saying, when if you will return your products at that time, we promise you, and we will have made sure that the system is designed in such a way that 50% will be applied regardless of what the current rules are in the system, okay? So in terms of doing the business analysis, that's an important question. Talking to your users saying, is this a promise towards future behavior? Meaning that even if the rules change between now and then, we will continue to fulfill our promise? Or is this a retroactive change, meaning whatever happened in the past is dead and gone, and we didn't make any promises, and we don't have to keep anything, and we just change it, and then you're done, okay? So if they tell you, yeah, we're making the change, it's retroactive, we're fine with that, then great, you can do the simple code that I showed you before. If they tell you what you've got is a promise, you need a slightly different approach to handling it, okay? So, this is one of the areas where we want a connection of state management as well as using some messaging or queuing systems. So, were any of you at the RabbitMQ session this morning? Okay, some of you, actually, about a third of you. So, RabbitMQ, as well as a bunch of other queues, support this concept of sending a message, but not sending a message right now. You're instructing the queuing system, I would like to have this message delivered at a certain point in time in the future. So I can have this type of, I call it a policy, a refund policy object, that when an order is accepted, I talk to a queuing infrastructure and say, 30 days from now, I want you to send a message that contains this order ID, which is the same as the order ID that I have in my state, and this refund percentage. So 30 days from now, the percentage refund of this order ID should drop to 50%. And in essence, what I'm telling the queuing system in this case, so you saw that, for those who saw that RabbitMQ discussion, you're not necessarily sending a message to somebody else. You can actually tell the queuing system, send that message back to me, okay? So instead of thinking about messaging in the sense of, I'm talking to somebody else, or if you're talking like you're thinking in terms of RPC or invoking a web service, think about it like invoking a web service on yourself some point in time in the future, but in a very highly reliable way, meaning that if your process crashes or the broker crashes or whatever happens, because in 30 days, it's reasonable to assume that machines might actually restart in the middle, that when we wake up, things will be persistent and durable, so we'll get this message back in the future saying, guess what? Your refund policy 30 days ago, you told me to tell you that the refund policy for this order ID should now be 50%. And 30 days hence, 60 days are up, and then it sends you another message saying, 60 days ago, you told me to tell you that for this order ID, it now only qualifies for a 0% refund. Okay? So in essence, what we're doing is we're taking the rules, the definition of the refund policy, as it was at the time that the customer made a purchase. We're taking that complete data set, we're throwing it into the future, and as time progresses, we eventually catch up with the data that we sent ourselves before. So that way, even if the rules change, and we'll see this in code in just a minute, even when the rules change, the rules will not change, will only change for new orders that are coming in, okay? Because in essence, what we're saying is, when time expires, it will tell us what the rules are. We're not invoking things, say, when you do your return, if you do your return at this point in time, we're not doing any calculation, we're just looking at the state that we have in our object, saying, what is the current state? If you return your products here, our current state is 100%. If you return your products here, the current state will be 50%. If you return your products here, then the state is 0%. In essence, we're not doing any time-based calculation when the customer returns their products, okay? And that's why it's safe. Because if the rules changed, let's say at this point in time, it doesn't matter. The rules only calculate when things get triggered, okay? So that's how we go about making a promise. And this is one of the things that, I don't want to say that you can't do this without queuing infrastructure. You absolutely can. I mean, that was actually one of the points that Alan made earlier this morning. Said, you know, you can use a database for this stuff, but in that case, you're using a database as a queue. Not using it for long-term storage. You kind of say, well, I'm going to put something in here because I know that a little bit later I'm going to need to use this data and then I'll take it out and then I'm going to delete it. So you can build, so everything I'm going to show you, both in terms of code and at a design level, you say, well, I can do that with a database. The trick here, if you will, is not whether the cylinder is lying on its side or standing on its head. Okay, that's not the big difference here. Okay, the big difference is that a queuing system makes it so that you don't have to write a batch job. You don't need to have something sitting in the background polling a database saying, has it been 30 days? Has it been 60 days? And we can take the logic that would have been in the batch job and put it into this object so that we have a full implementation of the single responsibility principle. We have one section of code that fully encapsulates the behavior of how refunds are handled over time. So you never end up in the situation where you change the online transaction processing part of your system, but somebody forgot to change the code in the batch job. Okay? By putting all of the code about the refund policy in one place, then also we can talk a little bit later on how much easier it is to unit test it once it's all in one object. Yes, question?
If you're relying on a queuing system to tell you when the refund policy is going to change, you're not going to have races in 30 or 60 days. So you get a refund at 30 days, and you can be processing that refund while you're getting a message saying.
Right. Right. So the question is, what happens if the customer clicks the button to return their products at exactly the same time as we're processing this message? Okay. Now, first of all, it's a great question to ask. Second of all, it's something that we need to be clear not only with our business stakeholders, but also in terms of development. Say, well, there could be a situation because a server was in the middle of restart right at the 30-day mark. So it could be that that message was actually from the web tier, it was sent first, but because the server was offline, it was stuck in some queue out over there, and the timeout happened to get in first. Is that really something that we want to have our system be susceptible to, or to have an impact on our end users? So, so I'll give you the technological answer first. The technological answer is that we can use infrastructure to give us very strong transactional semantics. So if you have two messages running, whether it's on two different threads or on two different machines, both trying to update the same state, that you'll end up with a concurrency violation. And then, this is something that didn't come up in the earlier talk today on RabbitMQ, but most of the queuing systems, if you have an exception while processing a message, then the exception bubbles up, means that you don't act the queue, means the message rolls back, and you process it again. So the fact that you have two threads, and this will be true for almost any database, just needs to be one that supports this concept of concurrency. That if you have two processes, two threads trying to update the same state at the same time, that a concurrency exception will be thrown, and then it'll retry a little bit later. Okay, that's the technological answer. Now, the business answer is to say, if we promise our users 30 days, then we shouldn't have this timeout be exactly 30 days. We should leave ourselves, some breathing room so that if something really bad happened, the server was offline or God knows what, then the timeout wouldn't be in 30 days, let's say a timeout for 31 days. Say if there was a race condition, in other words, the user clicked return their products at the same time that the timeout's happening, and for whatever reason they lost the race, then we're saying, look, you lost the race for 31 days. We only promised you 30 days. So whatever happens between now and then, this is our it is only through our good graces that you happen to win the race the last time on 31 days. But our business policy only grants you 30 days. So in general, when the business gives you requirements and says, do this in 30 days, do this in 60 days, always leave yourself a little bit of a fudge factor. And you'll want that fudge factor to be proportional to the expected downtime of your system. So if your system can be down for up to 2 hours at a time, then you should leave yourself at least 2 hours of fudge time, if not more, okay? Now, occasionally I get this in discussions, when I'm consulting with clients and the business stakeholders. Well, we want something done in 5 minutes. Like, okay, you do realize you're running on AWS. And running on AWS, you do not actually have failover time of 5 minutes. It can take easily 15 minutes, if not 30 minutes, for things to really get up again. So, for your infrastructure choice, 5 minutes can't be guaranteed. It will be somewhere between 5 minutes and 35 minutes. Now, occasionally you get a business stakeholder say, oh, well, that's unacceptable. The answer to that is, a very polite form of, well, pay up or shut up, pretty much. Saying either you give me the money to have infrastructure that is able to give you that level of failover time, or shut up about it. I can't spin straw into gold here, okay? Yes?
I'm just thinking, what if you project rules together with your message so that you can, still exactly compute elapsed amount of time?
Oh no, that's what we do. We pass the data saying what it is. Even if you pass the time, it doesn't really matter. If your message broker, if your messaging infrastructure itself is down, okay?
Oh, right.
And when it comes up, it takes some time for it to kind of sync up. It could be that the user returned their products, okay? And again, because of a race condition, they just got in ahead or they got in too late. So, recomputing the rules in your code over here is a little bit risky, again, because of the versioning thing that we were talking about before, okay? Saying, when you're out over here, how are you going to know to recompute the rules unless you actually have the rules that say 2040 or 3060? The whole purpose of putting the times and the rules into the queue was so that we wouldn't have to worry about reevaluating it, because then it's hard enough to handle this in the sense that I'm not doing the calculation in real time, and I can trust the information that I put in the queue before. But if I have conflicting information between the rules that I have in my code and the data that's coming from the queuing system, it's going to be really difficult to think about how do I change my code in a backwards compatible way. Okay? So we're going to get to this once we get into the code, which is coming really soon. Okay, but just want to get you guys thinking in that right kind of way of saying, if we have a future promise, then how do we figure out what times to put in there? As I said, there's the technological element of concurrency, and then you have that business element of fudge factor and making sure that that's going to align well with the downtime requirements or the downtime constraints. Nobody requires downtime, right? And implementing this is, hands on heart, I'm going to tell you, it's more code than this, okay? No question about it. This is the simplest code in the world to write. The only problem is, as I mentioned before, this code is dangerously wrong. The mitigating factor, or the, let's call it what allows you to write this sort of code is that potentially you can outrun the problems that you've created. Meaning, if you're working on a 2-year project, you can write this code and everything will be fine, and you'll be promoted to a different project in the company. Or if you're a consultant, you finished your 6-month contract and now you're at a different company. So you kind of leave a trail of problems behind you. But again, because most of the time the code takes much longer to go into production than it actually takes to write, this is why we end up having so many systems that have these sorts of problems inside. Okay? So again, I want to say, for those of you who are contractors, nobody will catch you if you write this bad code. Okay? And in many cases, you're under the gun and saying, look, we need this implemented yesterday. Like, well, either I can write these very simple 4 lines of code over here, or I can write the 40 lines of code that Udi's going to show me in just a minute. Let me see. 4 lines of code, nobody's going to know that it's a problem, and I'm going to be able to get out of here before anybody finds out that it's a problem. Or 40 lines of code, and then I have a problem today, because my boss wanted this implemented yesterday. Let's see. Pain today, and potentially no pain 6 months from now, so a low percentage chance. It's hard to pick, isn't it? But assuming that you wanted to do the right thing, this is not a class on ethics. Okay? Assuming you wanted to do the right thing, and or potentially you're just kind of sick and tired of writing the same boring code over and over again, like, hey, might as well use a queuing system, and this seems like a good excuse to do one, so that when I go to my next gig, I can say, I've also got experience in A, B, C, and D. That's called RDD for those of you who don't know. That's resume-driven development. So I personally prefer the CDD, the CV-driven development, because then you have DDD, right? You've got BDD. You've got ADD, of course, right? If you're in this industry, how can you avoid it? And then you've got CDD, so you have the nice first 4 letters of the alphabet already taken care of. So from here, I'm going to jump to code. And I'm going to build this up gradually. The code that I'm going to be showing you, you don't have to type it madly in front of you, write it. I put up a blog post today that has everything that I'm going to be showing you. Okay, so just go to my site. It's udidahan.com. Google Udi Dahan. It's not difficult to find me. The code that I built is written on a framework that I developed over the past several years to make it easier to write message-driven type systems and include all the types of functionality that we're talking about over here in a higher level API. And I'll be talking through that right now. The project is called Service Bus, and it's now part of the larger particular suite that I'm going to be also showing you in a minute. All of that you can find online, download it, play with it, and have fun with it. All right, code. This is the tricky bit because it doesn't want to duplicate my screen. So what I'm going to do over here is this. So I'm going to have half an eye on the projector and half an eye on the rest of you. Okay. All right. So this is the solution that we've got in front of us. I'm not going to show you all of it. I'm not going to jump directly to the service, the refund policy thing. But here is a high-level diagram of the thing that we've got going on. Let me see if I can full screen this. No, it doesn't like full screen. Okay. So just going to talk you through some of the basic building blocks. We've got a front-end MVC thing over here to just make it easy to test, to kind of poke this thing. The front-end MVC has a couple of messages that come out of it, a submit order message and a return products message that are going to this back-end process where we have some code that's handling them. The code there that's handling just doing very simple publishing of an event. So you have one of them that's publishing order accepted, the other one that's publishing products returned. And both of these events, as you can see, come into this refund policy object. And ultimately, the refund policy object, when it makes a decision, sends an issue refund command to this other backend. Okay? So ultimately, the logic of how we decide is over here, and this is what we're going to be zooming in on, where the output of that we're going to be seeing spit out over here. Okay? So this tool in front of you is something that we call Service Matrix. It makes it much faster and easier to build message-driven systems. You're kind of saying, okay, I want a front end, and these are the message types that I want, and it's going to be processed over here. And ultimately, it generates all of the underlying queues and routing stuff for you, so you don't have to worry about all of that crazy RabbitMQ stuff that you saw this morning. All of that is just taken care of for you magically. Okay? Now, we're going to go into that refund policy object and talk about, how we would build a type of object that is triggered by an order accepted event and handles a products returned event, making sure these two things are correlated with each other, and ultimately makes its decisions in such a way that, as we mentioned before, the rules are captured as this type of promise that is sent into the future that way. Okay? So, what we'll do over here is we'll pop into our refund policy object and view the code. And so there's a whole bunch of code that's already in existence over here. But what I'm going to do is I'm going to comment it out and build it up gradually for you so that you understand what it is that we're doing, and why we're doing it. Okay? And we'll squish that down. And over here we have our data object that says, for each order ID, we have a percentage that defines what its current refund would be if they would return their products at this time. Okay? So we have that persisted so that, again, when anything comes in, we'll know how to handle it. So there is our object. Here we have, again, our refund policy object, and I'm leaving the comments there so that afterwards I can, so if anything doesn't work, I can always pop that open afterwards. So, what we have is the code that handles the order accepted event over here. And for those of you that are wondering about the magic underneath, the code is open source. You can crack open in Service Bus and see all the magic that it's doing behind the scenes. In essence, the way that in Service Bus works is it reflects over your objects, and it uses the information about the type signatures to be able to build up all of its dispatching logic. So when a message of this type arrives, well, more accurately, JSON arrives, it deserializes that into a proper order accepted object, as you can see over here, that has an order ID. Okay? And this order accepted object triggers a new refund policy into existence, and then invokes this method over here. So what we'll do is we'll just do a very simple console write line so that we can see this in front of us, saying order accepted. And keeping in mind, going back to the picture that we have over here, that it's important that the products returned and the order accepted correlate with each other. Okay, so anytime you're doing any sort of cross-message correlation, you're going to want to have some application-specific ID that helps you tie these things together. So in this case, it's very simple. There's an order ID on each one of these messages. And in essence, what we want to do is to make sure that that order ID ends up in our data object. So there's our order ID coming in from the message. Okay? Make sense? So we get a message, we write something to the log so we can see it, we set the order ID, and now this is the point in time where we need to say all of our rules, the 30-day, 60-day rules, okay? We need to encapsulate that in our diagram from over here. It says we need to send a message to a queuing system, a deferred message saying, 30 days from now, give me back this information, all right? So 30 days from now, my refund percent needs to be 50. So for that, we have an API. It's called request timeout, okay? Which talks to the queuing system, allows you to either say at a specific point in time, so Thursday at 8 a.m. Remember everything that I told you at the beginning of this talk. Thursday at 8 a.m. in which time zone? Thursday at 8 a.m. on which geographic data center? Okay? Be very careful about that. So in general, let's just use a timestamp. Not timestamp, time span. There it is. From days 30. And now we're going to send a message back to ourselves, as we said, with what is going to be our new refund percentage. And at that point, it's going to be 50%. Okay? Where percent is very simply, extra semicolon over there. Percent is very simply a utility method that I've implemented on top of int to create a proper data structure around it. This is the DDD value object discussion, if you like. Instead of just passing around ints, saying, no, this is a percentage, and the percentage goes between 0 and 100, and that kind of stuff. Okay? And similar to that, we now have to open up another timeout that looks very similar to the first, but instead of being for 30 days, it's going to be for 60 days, where now it's going to be 0%. Now, it's very important that we open up, that we request both of these timeouts when the order is accepted. Okay? Why is that important? So that when the business comes to us 3 months later and says, change this to 2040, the 2040 change will only happen for new orders that are accepted. And that when we're going to look at the code that says, okay, how do we handle the timeout when it occurs? In essence, that code is going to be trivial. It's going to say, if we got a timeout, then all we're going to do is update our current refund percentage to whatever we got from the message. Okay? So, do that really quickly over here. So, public void timeout of percent. That's the state object. Okay? And here what we do is say data dot percentage equals what I got from the message. Right? So it doesn't matter if the rule said 20, 40, 30, 60, or however many is going on. And as time goes by, all that we're doing is we're saying, and now my state is what I said my state should have been in the past. Okay? Such that when ultimately the customer returns their products, okay? So public void handle, products returned, there it is. In here we can say, I don't have to calculate what my percentage is. All I'm doing is saying whatever is my current state is what the percentage is. Okay? So in here what I'll do is I'll, in order to know, to issue the refund, in essence I'm going to use the wrapper around my queuing system, which we call over here a bus object, to send a message of the type issue refund, where the message is, let's do it like this, where the message's order ID is what we have stored in our data, and the message's refund percent is also what we have stored in our data. Okay? So in this case, we're saying my refund policy object has decided that you qualify for a 23% refund. How did I come up with that? This code does not know and does not care. This code does not know and does not care. The only code that knows what your refund percentage is going to be is the code that was invoked at the time that you placed your order. So if at the time you placed your order the rule set was XYZ, that is what's going to be applied, regardless of how those numbers changed. Okay? So in this way, in version 2, so after we deploy this into production and the system is running and the business says, hey, change the rules, we can change the rules, change those attributes in there, take that new assembly, throw it into production, and know that we have achieved the intention of having 2 different rule sets running in parallel, but still only having one version of code actually running at a time. Okay? You all with me? It's not magic. Just using a little bit of messaging, a little bit of state management to kind of wire the things up, and then you achieve this sort of outcome. Okay? Now, because we have some state, as we mentioned down here, we will, at some point in time, want to clean this state up. Right? We wouldn't want to end up in a situation where we have a whole bunch of zombie records inside a database somewhere, and we don't have enough model to clean them up. So this is one of the things that, again, we don't need a batch job for, because we have this object which is being triggered as time goes by. So in essence, we can say, when time is up, we can check, is the state now 0? In other words, if we say at this point in time, you no longer get a refund, then we can clear out all of the state of our object. And that's done like this. So if the state is 0%, then we have this API called mark as complete. Mark as complete instructs the infrastructure saying, this long-running process is now done. Any state that you have for it can be cleaned up, okay? So that way you have this nice built-in cleanup logic to say that, well, 60 days later, the object's gonna say, well, that's all, folks. And off it goes and cleans itself up without you having to write some other batch process, which is pulling the database every once in a while to say, what do we need to clean up, okay? That's one element of it. The second element is this part over here saying, well, if the products were returned, let's say the customer purchased their products, and immediately on the next day, they returned them. Why? Because they thought better of it. Doesn't really make sense to leave all of those timeouts lying around and to leave the state of the object sitting in the database for another 59 days. It's going to have a little bit of logic in here that says, if the data, or sorry, at this point in time we don't need any if, it's really simple. We just mark as complete. If you return your products, that's it. This process is now done. We've told you how much of a refund you're going to get, and that's it. Okay, so now our process has also completed. So if you return your products after 1 day, that's it. After 1 day, it's done. Now, the interesting thing that we do over here, which is as a part of our mark as complete logic, going back to this picture, this is one of the things that the infrastructure does around your object, is that when you mark your process as complete, it actually sends another message. It talks to the queue wrapper on this end, and it says, any pending timeouts that you have for this long-running process, clear them out, okay? Why? Because we want to conserve resources. We don't want to have, imagine the case where you have, another 60 days where things are kind of sitting around unnecessarily, multiplied by the number of orders that you've got in your system, even though, a lot of those were canceled, okay? We're going to hold on to things for as long as we need, but no longer, all right? Yes, questions?
Can I ask, so the state is stored somewhere in the database?
That's correct.
What triggers the state to be updated after 30 days? When you issue the request timeout command, is it some defined message or?
Right, so the queuing infrastructure, after 30 days, sends a message to your queue, okay?
The message would stay for 30 days in the queue? In the
queue over here. Now, again, this is at an abstract level. There are different queuing implementations. So, for example, MSNQ, or Microsoft MSNQ, doesn't support deferred messaging. So, if you're going to be running this, one of the nice things about the Service Bus infrastructure is that it wraps all of those types of queuing systems. It says, even if you plug in MSNQ, we have our own implementation around it for the deferred messaging. But if you're using RabbitMQ, which we know supports deferred messaging, then we'll just lean on that. Okay? So in RabbitMQ, the message would actually sit in the queuing system for 30 days. If you're running on MSNQ, then we actually have a separate type of process that puts it in by default. We put it in a document database off to the side so that we're not overloading your database. And then we have in-memory caching and all sorts of smart things so that we don't pull that document database unnecessarily, to know that now is the right time to trigger the message, which will go through the queue, which then will pop out at the other end. You want to see how all this stuff works? Go to the site in servicebus.com, go to the resources, it'll take you to GitHub, you'll see the source of how do we do this on MSNQ, RabbitMQ, ActiveMQ, Azure Service Bus, Azure Storage Queues, we support a whole bunch of them. And each one has, slightly different details. But, so if the queue has implemented deferred messaging, then it already knows how to do that in a fairly efficient way. If it doesn't, then we kind of take over and handle that. Okay? All right. So one last thing that we're going to, well, I don't want to say one last thing, but let me just see if this thing is actually going to compile and see if I implemented all of the methods that I was supposed to. I think there's one that I'm missing. And that is what happens if the customer returns their products too late. Okay? So it's been, 80 days since they made their purchase. And they come to us and say, here are my products, I don't want them anymore. So because we said after 60 days we're going to clear out this object, there's not going to be any code that's kind of sitting there responding to that message when it arrives. But we'd like to. The fact that you don't actually get a refund does not mean that we don't need to respond to the user, right? The user clicked on the website, says, I've returned it. We need to give some sort of response to say, you don't get a refund, okay? In order to do that, we need to be able to handle the situation of a message came in that should have been associated with this policy object, but a policy object wasn't found. Okay, so that we have complete encapsulation of the refund policy over here. In essence, what we're saying is we have this interface. It's called, not over here, I handle saga not found. Okay, so when a message comes in to this endpoint, that for all intents and purposes, and how do we know for all intents and purposes, I'll show you in just a second, is supposed to have been handled. Right? We've got a method that says, here is how we handle the product's return, but that's only in the case where we actually have an existing instance. What we'd like to say is, if a product's return message came in, but we couldn't find an existing refund policy object for that order ID, still we want to do something, okay? So, what I can do is this. Where's that code over here? There it is. So here we just write a very simple handle of a general object, okay? Because at this point in time, we don't know which type of message it is. Now this method will only get invoked. This is sort of a catch-all, saying if all of the other methods could not be matched, and a message came in, then this is what gets invoked. And in here we'll say, if this message is a product's return message, meaning the customer returned their products, but we couldn't catch that at an earlier point in time, then this code gets invoked, and over here we can do pretty much whatever we want. We can console.writeLine, no refund for you. We can also, if you like, send a message back doing something like this. Bus.reply, new, no refund for you message. Okay? I don't currently have that input. So even though the state object is not there, we can still run some logic in the same object to say, this is the single responsibility. This is where we need to handle all of these scenarios. Okay? So right here, I'm not going to do that. We're just going to do a console writeLine and be done with it. And the last thing that we're going to be doing here, which I haven't yet done, is what I mentioned before is really important, is the correlation between the order accepted event and the product's returned event. In essence, saying we need to make sure that we're matching based on the order ID. Okay? So while a order accepted causes this thing to get started, we need to correlate, and there's this method over here. It's called configure how to find the saga. Okay? And in here you define a mapping. For whatever reason, it is. We're going to configure a mapping, and again, all of this is documented online, and all of the code that you're seeing in front of you is on my blog, just to give you a high level what's going on. So we're going to configure a mapping with the product's return event, instructing the infrastructure saying that this message, the product's return message, it has a property on it called order ID, and that should be mapped to our Saga's property that's also called order ID, right? We saw down there that in our Saga data we have an order ID. In essence, what this is doing, just to give you an idea of what's happening behind the scenes, this is instructing the infrastructure. when a message called products returned arrives, go to the database, in essence do a select star from this database, where the order ID is equal to the value that we got from the message. Okay, so it's just a glorified SQL statement, but instead of writing SQL in this code, we kind of keep it at a slightly higher level of abstraction. Okay, and now if I am incredibly lucky, all of the code that I just wrote, when I run this, is actually going to work in front of you. So let's give it a build, and well, the build succeeded. That's one step. Here are all the background processes. Here's the web front end, and I'm going to talk to you about this thing in just a minute. Okay. So this is the front end MVC site that, as I mentioned, is what we're going to be using to poke a bunch of messages into it. So we have this this template that we create for MVC project that has this tester built in that makes it really easy to create this type of property grid for every single message type that you have in your system. So you can say, okay, I'd like to send this type of message, I'd like to send that type of message containing these types of properties. So let's create an order ID 456, and we'll submit that order. And now we'll take a look at these background processes, and we see sales over here has received the submit order message. Hooray, right? And let's now look at the second one. And here is our backend saying order accepted. That's the code that we wrote before. Okay. And currently, when we look at the third one, it's not doing anything. It's saying, I didn't yet receive an issue refund, so what do you expect from me? Okay. Now, when we go back to this code over here, now we go to return our products. You know, this is happening within the first 30 days, right? So when I type in 456 over here, and I click send, and we go back to the first one. It says, okay, fulfillment has received return products. Okay, so we've received that first message. Now we look at our second one. It says, oh, it's still only got order accepted. That means I screwed up somewhere. And we haven't yet received, oh, actually we had an error over here. So something's failing. So I know what it is. I didn't write the console right in the second one. So that's one thing that's going wrong here. Second thing what you're seeing here is this is that rollback logic that I talked about before, where I said if it fails processing a message, if an exception occurs, what it does is the message rolls back. What we do as a part of this is that we catch the exception and log it. You know, that's the best practice. Then it has this sort of long-running, I don't call it long-running, it has this exponential back-off behavior. It says, you know, if I couldn't process the message the first time, then I'm going to wait a little bit, because it could be that what I have here is a transient exception, could be a deadlock in a database or something. If you just give it a couple of seconds, it'll work itself out. But eventually, after it exceeds all of the retry steps, it says, look, you know, I tried and tried and tried again, but I just can't make it work. Then what happens is it takes that message, moves it to an error queue, so it frees up the queue, the original queuing flow, and tells you what the problem was. And this is where it's really helpful to have a tool like this other one that we got over here, okay, where it shows you the message flow of your system. So let's check our, what was it, the back end, there it is. And here it tells me, okay, so you had a return products event that invoked some code over here, which in turn sent an issue refund message, but that thing failed. It blew up. So I can pop over here to the errors, and maybe it'll tell me what went wrong. Seeing maybe it's not doing that. It said system.null reference exception. Okay? Happens, right? Happens to the best of us. But the important thing that happens here is that we haven't lost this message. Okay, so this message over here, I can just squeeze that down over there. Let's see. Products returned, order accepted. Let's try doing search by message ID. Let's not find that one over there. Okay, there it is. I can look at the body of that message, and there it tells me, let me zoom in on that for you. Here's our issue refund command with the order ID 456. Say, okay, this is the actual message that blew up. Now, this is one of those things, again, Alan mentioned it this morning. If you have sensitive credit card information or things like that, you're going to want to encrypt it. With Web Service Bus, we have a simple historical way of doing that, where you can just kind of put an attribute on a property and say, I want this thing to be encrypted, so that ultimately the infrastructure handles that, and any administrator that's looking at this, while they can see the business data saying, okay, we had an issue refund, or we had an order that was submitted, or whatever, they can't actually see the sensitive information. Okay, that's something that security guys tend to get really up in arms about once you start talking about messaging and say, well, if we had SSL over HTTP, it would be safe, but if we have SSL to the broker, but the message just sitting there in the broker, if an admin can take a look at that broker, then all of the data is exposed. SSL is not enough when you have data at rest this way. So encryption is something that becomes important. And incidentally, once I figure out what the problem was over here, so let's stop debugging, and I'll go over here. It says, okay, now I know it's the issue refund processor, right? This code is the one to blame. It told me in the code over there. So I'll go take a look at this code, and it's saying, okay, apparently, my guess is that I didn't set the percent. So it's saying, what's the percent? Well, it's null, right? It's an object that you haven't set. So now I can go back and see what did I do wrong in my refund policy. I said, if you return it, then the data percent over here. The problem that we have is that I'm taking this object from my data object, but it wasn't set at the beginning, right? So when my object started up, it said, well, somebody returned their products, how much of a refund do they get? I didn't say, right? So now I know, okay, stupid, data.percent equals 100%. This way I know that now everything's going to be okay, all right? So now we'll run this again, so we can close this down. It's really nice having these sorts of tools. Anytime you're building a message-driven system, I mean, it's great having everything loosely coupled. All of the things that Alan mentioned this morning are absolutely true. Development is a whole lot faster. You have different teams working on different technologies. But sometimes you really need the ability to see the thing flowing end to end, to be able to say, okay, this is where it blew up, and to trace it back and see where the source of the problem was. So, running this again, hopefully, this time it's going to work better. Oh, but I didn't do the console write line. I think I forgot that bit over here, right? So, console write line, products return, because we didn't see that before. So, close that first one. That. Go back to our web front end, send the message. This time we'll do a different order ID, 888, and we'll send that one off. And then we'll do 888 over here, and we'll send that one off. And now when we look, we'll see over here both the orders accepted and the products returned. Fantastic. And we see over here a message that says, issuing refund for order 888 for 100%, which is exactly what we expect. Okay? And now we can look back. It's very useful having this thing over here. And we'll get rid of that. And going to the top and taking a look at the issue refund. And now when we look at the issue refund message, we see that it actually has a percentage value, which is nice. We can look at the flow diagram, and we see over here let me squish this up a little bit. It's hard to, nobody programs at 1024 by 768, right? So here we see that the flow was successful, right? So it went through all of the steps. And we can actually click through to our refund policy object. You see that it's mentioned out there, which shows us, let me squish this back over here, the refund policy and all of the messages that flow through it. So we can take a look, and it shows me the message data came in, order message 888. The Saga state was updated, and it set the order ID, it set the percentage value, okay? And also, it, down here, had a timeout request, okay? Magnifier's not working very well. Okay. And then, when the products were returned, well, at this point in time, the Saga didn't need to do anything, but then we issued a refund, as we saw over here, order ID 888, and percentage equals 100. Okay? So, and then finally, the Saga was complete. Okay? So, now I want to take this to the next level. This is nice. We made that all work. And as you saw, I didn't really have to be an expert either in RabbitMQ or MSMQ or how to set up routing keys. All of that stuff is handled for you behind the scenes. And you're more focusing on, at the high level, what's the flow of the messages through my system? What are their message types and what data do they carry? And ultimately, my business logic over here. So the last thing that I want to talk about is, well, it kind of sucks that when the business wants to change the rules from 3060 to 2040, that they actually have to go and talk to a developer and say, please, can you open up the code, change these values, and redeploy, right? So we like to externalize that. And so the thing about this infrastructure is it all leans very heavily on containers, IOC containers, dependency injection, and all that. So what we can do is, in essence, say that this data set that we have over here fundamentally is a dictionary between time spans and percentages. Saying when your time span is 0, right, when you get started, the percentage is 100. And then another time span value, key value, key value. So in essence, we can declare on our refund policy object a dictionary of, why did that pop up over there? Time span and percent. And we can call this our, say, our refund definitions. So I'm lazy, so I'm just going to do this using property injection. In essence, I declare this property that I expect will be defined by an external object and injected into my code over here, okay? Property injection, if you haven't done it before, Google it, lots of information online. And then, in essence, so either I can assume that I'm starting at 100%, or I can say, no, actually, if you want to define 100% at time span 0, then stick that in the dictionary, okay? So I'll get rid of this, and in essence, what I'll do is I'll say, for each key value in my refund definitions, what I'll do is I'll request a timeout for the key, and passing back to myself the value, okay? And this way, I have fully externalized for my object what actually the rules are, whether it's 2040 or 3060, or whether there are 3 of them or 12 of them, not really my problem anymore in this object over here. And now all I need to do, in essence, is to read the definitions either from a database or from a config file or from wherever you like, and then tell the container to inject that in here, okay? So I'm just going to write a very simple object down here at the bottom that at startup of this process, it's going to inject those values inside it, okay? So, sorry, not over there. So most containers tend to have some sort of bootstrap interface API that you can connect to. In Service Bus, where we wrap a whole bunch of existing containers, I'm just going to write a bootstrapper class that implements the I need initialization interface. Okay, so what happens at startup, we scan all of the types, we find the things that say I need initialization, and we tell them invoke your init logic. And in here, I can go to that config file or wherever and pull out a dictionary of time spans, and percentages, and say this is my data. And I can get this from, again, config file database, wherever you do the lookup. Here, just to have something that works, I can do it like this. Just new that up, right? And then data.add time span from days 0, 100%. And data.add time span from days 30, 50%. And last one, time span from days 60, 0%. Okay? And now that I have my data structure full, I can tell the container, and we have a wrapper on the container. It's kind of ugly, I apologize. We're making it better. Configure.instance.configure property of the refund policy object, setting the policies, we call them refund definitions, if I'm not mistaken. So it doesn't like configure property. Why doesn't it like it? Just a second. Configure instance, configure property of refund policy. Okay, wait a minute, I think I know what it is. Refund definitions. And then the data object. Do you like me? Oh, it's a private property. Yes, whoever told me that, thank you. So, make that public. And then, now this code compiles. So now we can see how we can externalize the definition of the rules from the object that's actually evaluating them, while still retaining all of the good stuff that we wanted before. So it could be as simple as, somebody going to a config file and then recycling a process, and you're done. Or there's certain containers that you can actually register a func in them, meaning that every time that the object is resolved, you could actually do a lookup to a database, okay? So if you wanted to have some sort of back end that the user could, update a database, and then the Saga in real time would change itself, that would work as well. One thing that I want to mention, really, really important, that when you're doing this, make sure that you don't open up a timeout from a timeout, okay? So if you say wait 30 days and then wait another 30 days, when the rules change, you may end up waiting 30 days and then only another 20 days, okay? So if you want to fully encapsulate the rule set, think about that from the perspective of all timeouts should be requested at T0, okay, when the process is triggered. So there's nothing magical in this infrastructure that is going to make your implementation right. We just give you some building blocks so that you can do the right thing, but you can just as easily do the wrong thing, okay? Again, I want to reiterate, some of the advantages of this, single responsibility principle, or maybe now's a good time for me to go back to my slides, okay? All right. So, you don't need any additional processes for cleanup, right? You don't need some sort of batch process going to the database and saying, has it been 60 days, has it been 90 days, and making sure that the batch process is updated every time the rules are updated, okay? Single responsibility principle, high cohesion, I don't think that I can mention that strongly enough. In too many systems, I see code that gets fragmented because, well, this isn't running at the same time as that. It ends up being in a separate code base. So if it's the same logical responsibility, and that's something that I found a lot, when talking to business stakeholders about things that are policies or long-running processes, things that not all the code is always invoked at exactly the same time, that is one of the places where most developers fairly frequently drop the ball on single responsibility principles. And the bigger the system that you're building, the more handles these types of scenarios of over time, the more your code can be dangerously wrong. It can look like it's working correctly, but it ends up working wrong. Now, I know all of this was sort of a lot to take in. This is a really big topic, but some other considerations that I want you to think about. This is not a silver bullet, okay? Number one, there's no such thing as a silver bullet. But number two, while this is a great pattern, occasionally there may be a situation where the business comes to you and says, you know, we screwed up, right? We gave you the wrong requirements. And while it's great that you implemented the system in such a way that you know, you're fulfilling your promises to the customer, we actually have to go back in time and undo the promises that we made to the customer, okay? That's not going to happen frequently. Sometimes it's going to be the kind of thing where the business comes to you and says, look, we screwed up, but for the majority of our customers, it's not a problem. But we have one or two really big customers that this has a huge impact on. So we need to go in and change it just for them, okay? When this happens, there is no magical implementation technology that's going to solve this problem for you, okay? So all of the timeouts that I talked about over here that we're doing, so in a queuing system, and it depends on which queue you're using, you can often query it, say, okay, give me the messages, but not from the perspective of, I would like to pull them out, meaning consume them. I would like to peek into them. So find me the messages in here that have, you know, this order ID for that customer, and then I'll go in there and I'll manually change the refund values. Or I might actually consume them manually and then send other messages in their place, okay? When we're running on top of MSMQ, we use a document database. And then you can, again, similarly, query the document database and get this information and manually tweak it, okay? So this kind of stuff, it's not a black box. On the rare cases where you'll need to do that, you still have accessibility to make those kinds of changes, okay? The other problem that we had that comes up occasionally, the scenario that I showed you before, where in this code over here, when we forgot to set the original data.percent, and as a result of that, the message that was issued, the issue refund, blew up, okay? So in that sort of case, we're saying, you know, it's not a business problem, we developers screw that bit up. Sometimes what you can do, when you find out that there's a problem, in essence you can say, well, because the message processing failed, you know, let's get rid of that message. Let's get, you know, all of the timeouts have expired, okay? So we go back to our original object, so we change the code here, and then we can, in essence, go to our audit log, and this is something that most queuing infrastructures have. It's you know, something that's called journaling. In essence, every message that comes in, they hold on to a copy of it. So you can take that and say, you know, we screwed up in how we handled this original message. Let's throw away all of the work that we did and redo that work. In essence, replay the order accepted message that we received 60 days ago, 90 days ago, whatever, and then trigger this process again, only now it's going to have the correct logic in there, so that when it flows out, and then we can re-trigger again the products returned, so that they happen at the right point in time, and then say, oh, okay, you know, we fixed this problem. So having loosely coupled messaging infrastructure containing this sort of audit log makes it very easy to say, if there was a problem, where was the problem? Help nail it down. And then once you know where the problem is and you can deploy a fix, you can replay messages, okay? So whether it's a failed message or any other message. But like I said before, in terms of the questions to ponder is well, what happens if the business tells me that the requirements were wrong? What if they said it was a promise and that it's actually retroactive? You know, you really do the best that you can. This implementation style optimizes for a certain type of requirements, but you know, if your business stakeholders are giving you the wrong requirements, and the system has run that way in production for long enough, in essence, you know, you've garbaged up your database. Okay? Now, not necessarily garbaged up in the technical sense of the word, but in the business sense, you've calculated the wrong values and you've stored them. You called out to third-party web services and communicated to them the wrong values. It's not easy to roll back the rest of the world when your code was wrong. Okay? I mean, it's great that message queues have this nice little feature of, you know, if my little part of the world blew up, that can roll back and try again. You can't always do that with external partners. That's ultimately people getting on the phone and trying to unravel problems and just to make sure that I'm not communicating any promises about what this pattern might give you. It doesn't solve those problems. If you have those problems, that's on you, which is why the requirements analysis is so important. Okay, so very useful pattern, very interesting way of thinking of it, and that's my cue to end. So thank you all very much. Hope you've enjoyed it. My website is udidahan.com. There's a blog with all of the information on there. And all of the infrastructure and stuff that you're seeing, it's available. It's called in Service Bus. It's available at the site particular.net. If you have questions, feel free to come up and ask them. Thank you all very much. The code is kind of, it's kind of handed off to the most junior developer. Here, write this batch job, clean that crap out of the database. It doesn't have to be that elegant. If you don't TDD, BDD, DDD, if you don't DD it, you're fine. Just kind of make it work. So you get all of this code that's going to go into the database, scanning through a list of something and said, if something happened in the last 24 hours, then do this. If something happened in the last 3 months, then do that. So a lot of time-based requirements, you don't necessarily see them kind of glaring in your face in the online transaction processing part of your system. A lot of times they're kind of sitting there in batch jobs that are pulling the database once a night, and then in there they're kind of checking time-based things. And again, the problem being that it's often written by the most junior people in the team, and that code isn't really thought of as part of the system. So if you make changes to the logic in the part of the system that's writing the data to the database to begin with, oftentimes we forget to handle the batch job part of the code as well. So even if you don't see it glaring in your face where your business is saying, hey, look, here's a time-based requirement, sometimes go look for it in the batch jobs and you'll actually see quite a lot over there. So we're going to take one as an example from the retail domain. I love the retail domain because most of us have had first-hand knowledge and first-hand experience as users in this domain. So classical example is you bought a product some time ago and now you want to return it and get a refund. Okay? So fairly simple type of requirement. And now the business says, look, we have these rules that say under which conditions will the end user get a refund for returning the product. So it could be really simple stuff, starting out with something like this. Here's some pseudocode type stuff that says, all right, well, when you get the time that the product was returned and you know when it was purchased, check to see if it was in the past 30 days. So if somebody returns their product within 30 days of a purchase, they're going to get 100% refund. If they return it within 60 days, so between 30 and 60, then they get a 50% refund, otherwise no refund at all. So it's the kind of logic that, again, you can have batch job going into the database, looking at the times that products were purchased, the time that they were returned, and then performing this fairly simple calculation and then deciding, okay, this one is eligible for a refund, that one isn't eligible for a refund, and we're done. It was last year or 2 years ago that Argentina decided all of a sudden that they were not going to observe daylight savings time. It's just, presidential order, no daylight savings time this year. It's kind of hard to code for those situations. So you will want to understand that anytime you're doing something with time and your users may be in some part of the world that decides unilaterally to not observe daylight savings time or to observe it on a different day, again, your code can start running in weird ways, especially if you have things that, some part of your system is running in time zone A, persists some data to the database, something else is reading that out, and is assuming that it's in the same time zone, it's in the same daylight savings time setting. This is the kind of stuff that hardly ever pops up in testing because nobody ever thinks to fiddle around with time zones or daylight savings time on the machines while they're testing the system. So it's something for you to think about, just to kind of get your frame of reference of how long we in the software industry have been having support in our programming languages for operating on, date, time, data structure type things. And the fact that the problem isn't solved yet today, okay? And really all I can tell you is if we haven't solved it up until now, we're probably not going to solve it by the time your project is done, okay? So this is nice big risk for you to go back and say, what are we doing about it? Now, the next step up, for those of you who are thinking of running in the cloud, is the topic of clock skew. Okay? And this is true for almost every geographically distributed system, that different machines that are in vastly different areas on the planet, you can't keep them 100% in sync in terms of the clock. So there is network time, etc., but the way that machines drift from each other in terms of, it's called clock skew, is really unknowable. So if you want to build a system that is absolutely bulletproof in the cloud, running in multiple availability zones, then you're going to have to totally stop using the concept of clocks or time that is built into base class libraries or the runtime. And you're going to have to come up with your own representation of time. Amazon did this a while ago, wrote a very nice paper on it, called it Dynamo, which served as the backbone for their Amazon DynamoDB, where ultimately, for example, in a unit test, until when you actually used it in your code, then your unit test failed. And that's actually good news, is when you actually have a unit test that's doing that, because then it will be an indication that when your system ends up in production, this is going to be a problem, all right? Now, so number one, anytime that you yourself are writing code that's using datetime now, or you see anybody else writing code, give them a nice little slap on the wrist, or program something into their machine to give them an electrical shock when that coding pattern is matched. One of the nice things that Microsoft has coming out in VS 2013, if you haven't heard about it, it's called ROSLM. It's their compiler as a service feature, which allows you to write little rules to be able to say when somebody writes a certain bit of code, whether you want that code to be allowable or not. So eventually I'm going to get around to writing a rule on top of the compiler as a service, so that every time that somebody writes this, their code will not actually build. Okay? So what's the problem with that? Well, you need to take a step above that. UTC now is a little bit better. It's kind of, it doesn't look evil, and it kind of pretends to be nice, kind of like these guys over here. But if you get into the details, even there are some minor problems. So UTC now ultimately is saying, first, we're dealing with the issue of time zones. Okay? So when you're talking about a system that needs to be deployed to more than one server, and let's face it, most software these days is not only ever going to run on a single machine, then you have to deal with the issue of time zones. More specifically, the fact that not necessarily are all the machines that are in your server farm going to always be set up in the same time zone. This becomes more of a problem when you have more than one data center or more than one administrator. Or just somebody's actually changing the time zone of the machine. Something small like that can cause your code to start working in weird ways. So next step up, make sure that in every place that you are going to do something with datetime now, replace that with UTC now, and that will help you take a step forward. The other issue to deal with is anytime that you're thinking about time in your system is the whole issue of daylight savings times. As we know here in the UK, we have recently moved turning on daylight savings time. And, but of course, that's out of sync with the rest of the world, right? Different countries decide or decide not to observe daylight savings time at different points in time, and also that changes from one year to the next. So I think it was. All right, good afternoon, everybody. Welcome. I hope we're recording in the back there. Thanks for coming after that big heavy lunch. Although they kind of force you to stand up while you're eating it, so it kind of goes down a little bit more quickly. This is the forced DevWeek logo on the first slide. And I'm going to switch to the actual slide that has this nice cool little animation. We're going to be talking about this thing called programming in the fourth dimension, and this is the little icon that I like to use for talking about the fourth dimension. For those of you who aren't familiar with this, this is a four-dimensional cube. It's called a tesseract. You can search on Wikipedia and read all about it. The reason that I use it clearly in terms of fourth dimension is because it has this element of time. And the thing about this, and don't stare at it too long, it'll kind of turn your brain to mush, because your brains aren't really wired for this kind of stuff, is it's a cube that over time is kind of folding in on itself and turning into the same cube. And that's really going to be the topic of this next hour and a half together, is talking about the element of time when we're programming. Starting from the very basic stuff that I hope everybody knows and quickly checking that off, and moving to the more interesting elements of time. Now, full disclosure, when I went to uni, I failed the course on relativity twice. Okay, so I'm definitely not the expert when it comes to how different objects change their mass and how speed and time, all of that is interrelated. We're going to take this from a very much more basic programming perspective. And from there, we're going to move on to different ways of thinking about time, programming about time, requirements analysis, and ultimately we're going to implement things, some patterns that you can use, and frameworks that support those patterns to get you guys up and running really quickly. So, starting off with the absolute basics, date time now is evil, okay? It is just about the most evil thing that you can create in your system, which is why Microsoft made it part of the base class library. Because, I mean, it's so trivial to just immediately start using it, and, it compiles, it runs. Even if you write some unit tests, there's a pretty good chance that those unit tests might even pass. But as things start to take a little bit longer, then comparing date times to each other starts to break down. Because if enough ticks go by between when you set date time now, if everything is tracked with, we call it vector clocks. You could think of it as a kind of large version number. However, the challenge around that is when you're building geographically distributed systems, is when you can no longer count on time and you've got all of these funky little vector clocks, your programming model kind of turns on its head, okay? So we're not going to be talking in this session because this is like 5-day course material. This is not 50-minute material. Just to give you a sense of the fact that, again, this problem is, not only is it not solved, but the bigger the system we try to build, the more unsolved it fundamentally is. And the more this problem becomes your problem, and again, the bad news being that when you're building a system on your own machine, everything works fine. When you're running all of your unit tests and you're kind of fiddling, everything works fine. And it's only when your project is 99% done and you're 2 weeks away from going to production, and things are installed and now things are working weird, that all of a sudden you start tracking it down and you find out that for whatever reason, when you spit out the clock ticks of the various time zone pieces, they're not in sync the way that you thought that they are supposed to be. So that's just to tell you that I like to start my talks with bad news, okay, to get people in the right frame of mind. Software sucks, okay? Programming, you might think, oh, cool, we've got the cloud and we've got all of these libraries and frameworks and it makes programming more productive than ever before. Like, yeah, but the problems that we're trying to solve are growing so much faster than the tools that we actually have available that we're actually falling farther and farther behind compared to where we were 3 years ago, 5 years ago, 10 years ago, okay? So now on that optimistic note, let's talk back on the requirements side of things, where even if you're in a case where your entire system is co-located and all the machines are in the same time zone, and you're under the most ideal possible conditions, even there are some risks around how you go about handling requirements that explicitly talk about time. So one of the places where we see a lot of these is batch jobs. Who's got a batch job in their system? Yes? Okay, bunch of you. Now, batch jobs are kind of like the black sheep of the family. Nobody really loves them.